Hi, I'm Steve Mosier, and today I'd like to demo for you my solution to automatically connect AWS transit gateways to a secure, intelligent routed network. So first, I put a few slides together, and this one is an overview. So this shows the transit gateway as a blue box in the middle of the screen. Now what I've found the transit gateways are really good for is that inter-VPC, that intra-region inter-VPC connectivity, okay, because they're very easy to connect to. So for instance, an application owner runs their application within a virtual private cloud, and that virtual private cloud needs connectivity to the enterprise network. So that cloud could be like either dev, or it could be production, or it could be some other type of traffic that needs its own segmentation from other types of network traffic, right? According to your organization's security policy. So for instance, if we had production traffic in the cloud, we might have a transit gateway that supports that production traffic. So I would deploy a transit gateway for production. So it would have been, for instance, like different VLANs and a VRF for that. But here, what I've done is created just a TGW with a default route table, and that default route table for that TGW would be production in this instance. Now the TGWs can have multiple route tables, but you can have 5 TGWs, and for my automated solution, I figured that 5 different types of traffic is probably enough for most users, for most accounts. If you need more, then what you would do is build different route tables per TGW, and this Polar program would then go ahead and identify TGWs based on their route table. So there's a way to do that. But to make things easy, I set up the TGW with the default propagation, the default association to the default route table, and that just makes things much easier. All right, so that's the transit gateway. Now what we see to the left here are multiple VPCs. So for instance, this could be application A, application B. This could be some kind of services like LDAP, NTP. What other services are out there? Many others, and just on and on. These VPCs are attached to the TGW through attachment points, which is very easy to do via console, CLI, or SDK. So the app owners would connect to the correct TGW in this example, but then the TGW needs the ability to get to other regions, and right now there isn't a way to do that. So what I'm going to do is connect to Cisco CSR routers, which can handle the encryption between regions, which can handle the routing, which can handle the dynamic virtual private network creations. Okay, there's another piece too. So the TGW could connect to a direct connect or a direct connect gateway, but right now that traffic isn't encrypted. So most customers that I deal with, they need encryption between the cloud and their enterprise. So these routers can handle that as well. This solution scales greatly because the TGW can handle 50 gigabits per second. You're going to need, if you're going to leave the region at 50 gigabits per second, whatever you connect to is going to have to be able to handle that. And the only way that I've found to do that is through the equal cost multipathing of the VPN attachments to multiple routers that can, aggregate up to that 50 gigabits per second if you needed that. So you have to use the ECMP, and you have to use the VPNs for that, because if you created a VPC and loaded it up with virtual routing nodes to provide the encryption and the routing decisions, you couldn't do the ECMP. So I believe it's you create a route that says, like, say default out or to your enterprise CIDRs, and that can point to one of them. So you're limited by the size of that routing instance. So what's good is the VPN allows you to connect multiple VPNs. So that's how the TGW and the Cisco CSR1000v or the SD-WAN V edges or C edges, which I'll make a demo of here in the future, could really add value to the TGW. So one, it's for inter-region traffic, it's for traffic back to the enterprise, and it's secured encrypted traffic as well. All right, so in this example, there are 4 VPCs connected to the TGW. We have routers that can support 4 VPNs each. So that's 5 gigabits per second per router. So in this example, this region has 10 gigabits per second capacity for ingress and egress together. Okay. So the Polar program goes through and it finds different instances. So these are the CSR1000v routers, and identifies different tags. So it has to have these tags here. This is the program key. So any instance that has this tag key value, this key right here, this is something that you configure. It's in the config.py file. That's how the program knows that this router wants to be a part or can be considered a part of the program. Then you could have different values for different segmented traffic. So this was where you could have dev or production. I just called it TGW for this example. So if there are routers that have the appropriate key values, then the TGW has a key value. Now the program knows that there's routers that can service the traffic from the TGWs. If the router has a tag of it's eligible for VPNs, VPNs can be created to it. And this is how we know how many VPNs can connect to the router. So this router is a C5 2x large, and the IPsec performance is actually 6 gigabits per second. But because I didn't deploy that on the hourly, but I used a smart license so I could save money in the long run, my smart license for this one that I had was 5 gigabits per second. So when the router was deployed, there's the peak performance, and then there's the license throughput. And when the tag is created for the router, it's the lesser of the two, so you're not limited by one or the other. And you can have intelligent VPNs created. So one of the functions of the Polar, as it runs, it sees there are routers that'll support this TGW cluster, and there is a TGW that has the same value as the router. And the program says, okay, well, I'm going to run through. Okay, you had 5,000 megabits per second. They weren't used. I'm going to go ahead and create a VPN. Then it knows it's been knocked down to 3750, but you could add another VPN at 1.2 gigabits per second, and it does that. And that's 2,500 megabits per second. I'm going to go ahead and add another VPN. Now I have 1,250 left. That's the 1.25 gigabits per second. And I'm going to go ahead and build that 4th VPN. So once it figures out how many VPNs can be built, it creates records for it within the program, and then it executes on those records through multiprocessing. So it builds all of the VPNs. If they're successfully built, it will go ahead and configure the router for those VPNs. And that's part of the Polar function. Here's an example where, say that these VPNs were created and I terminated my router. So the router is going to have shutting down as its status. So the next Polar cycle that reads the router says this router is shutting down, but it had 4 VPNs created already. So it sees the tag and it had 0. And well, if I was stopping it, then it would add the tag 5,000. If it was being terminated, it wouldn't be able to add it, probably. But so if I stopped it, it would also get rid of the VPNs, and it would add that value back to it. So what happens here is this allows for you to add more routers for capacity. And then if you don't need the routers anymore, you can terminate them or stop them. So you could start them again, would be the idea. And it'll reduce the capacity. You won't be charged for the instances running, and you won't be charged for the VPN attachments. So you can expand and you can collapse. That's very cloud friendly. So here's an example of an architecture. So we have 2 different regions, one on the left, one on the right. At the top of the screen, we have 2 enterprise sites. They're all connected to the same dynamic multi-point VPN, the DMVPN. So they all have IPsec VPN reachability to each other, and they're all sharing routes. Okay, so you have many different application VPCs. They all have the VPC attachment to the TGW, and then the TGW connects to the routers. So these could all be production. I could have a whole other setup like this with a different TGW that's labeled for dev for instance, then the dev VPCs would connect to the appropriate, obviously the dev TGW, and then that would ride the dev circuits, or however you're segmented, maybe dev LSPs back to the enterprise to the dev VRFs. So this is an example of region-to-region connectivity and region across. Here, this would be the internet to a site. This is a notional architecture. So here we have the same idea. It's deployed in different regions. Let's say this is all production. So these are production TGWs in 4 different regions. It has the routers set up. Looks like 1, 2, 3, 4, 5. So 5 routers with whatever the capacity is there. And here at the bottom we have 3, and then I have the dots here because it can scale out to whatever you want. So scale out, scale back. The VPNs are connected here. So this is probably C5 larges. It will support 1 VPN. So remember, the program will always try and fill up the potential, the capacity of the routers. So the idea is that you, as IT, you deploy the type of routers that you need, and you know that it will have as many VPNs as can be created for the capacity of the router. So this is an example of a region. You have the user VPCs, VPC attachments, the VPN attachments to the routers, however many there are. And then, in this example, we have 2 VPN clouds. One is for the inter-region connectivity, and then one, according to this region, DMVPN 1, is using a direct connect. So this would have a different front door VRF with a different default route and a different VPN, DMVPN overlay that connects over this. And here there are 2 enterprise sites that connect to that. So inter-region uses DMVPN2, and then there's a direct connect at this region that goes to the enterprise. So not on this diagram, but there might be other clouds that are connected to each of these other regions for crossing their direct connects at their locations to get back to the enterprise. This is a notional architecture. This would scale greatly. It would have inter-region connectivity, encrypted inter-region connectivity, and encrypted to enterprise connectivity using direct connects. Okay, so this is the demo that I'm going to show you today. So I have 2 regions. I'm using US East 2 and US East 1. I went ahead and I used let's see if I could find it, this cloud web program that's shared on GitHub, and went ahead and deployed a DMVPN cluster, and I called it TGW. So if I could pull up the dashboard for that. I made a few changes to my original standalone VGW to CSR solution and added TGWs. So what I did is I deployed a cluster. It's called TGW. It's in US East 1, so Virginia, in 2 availability zones, and this is Ohio. And so these routers are out here right now. They're marked as not eligible for VPNs. Okay, and I have 2 TGWs, both marked with the same cluster. So these are TGW marked TGW cluster, and one in the east, and one in Virginia and one in Ohio. All right, so let me hop over to Amazon just to show you. So right here, this is Ohio, and I have 4 VPCs deployed, the 2 router transit VPCs, and then I have an app A VPC and an app B VPC. And then in Virginia, VPCs, I deployed an extra transit VPC in here. Okay, well that won't matter. I have an app C, an app D, and then my 2 transit VPCs. I'll have to clean that up. Let's see, so here in Virginia, I have app C and app D, and I've already created the TGW, so let me go ahead and pull that up. Here's my transit gateway, and I have 2 attachments already created. So app C and app D, and they're connected. So all the routing has been, so the route tables have the appropriate routes, and I'm going to go into the routers, which would just be the instances. Can't see it. Okay, so here's app C. I'm going to go into app D and show IP interface brief. And what I'm going to do is show that through the transit gateway, these application VPCs can ping each other. So I'm going to ping 10.255.0.87. All right, so we can ping back and forth through the transit gateway. And now I have app A and app B, and they can't ping each other yet. Okay, so I'm going to take app B and I'm going to try to ping app A. So gig 2 to gig 2, these are internal VRFs, private route tables, and right now B is connected. So I'm going to go ahead and go into app B. Oh, I'm going to show you there's an attachment created for this. So app B is available, and what I want to show you is how simple it would be for the application owner of app A to connect to this. So if I was the app A application owner, I would go in to create an attachment. I would pick my TGW, the appropriate one for the for whatever cluster I had. So I'd probably label this production or something like that. In the future, I want a VPC attachment. I'm going to call it app A and select the VPC. So I'm going to connect it to app A. So as the application owner, this is very easy to connect to this TGW through the console. Then I have to select one subnet from each availability zone that is created for my VPC. And here I only have one, so this is pretty easy to do. So I create my attachment, and now, as the application owner, once this is available, this transit gateway will show up as an endpoint for my routes. So what I'm going to do is go into the route table for app A, so that private route table, and what I would do is add, very simply, a default route, and I'm going to point it to that transit gateway. And the status of that transit gateway is still pending. So I can't do it just yet. So what I'm going to do is cancel here, go back to transit gateway attachments, and just watch this. Okay, so that might just take a second. So what I'm going to do is show you the puller program. So this is the actual function that's running right now to create. So this is that instance that I needed to delete. But it's running on a 10-second loop. It's running through, it's looking for instances with the appropriate tags, it's looking for gateways with the tags, and if those instances have available bandwidth for VPNs, it'll create the VPNs. So let's see what's deployed. I'm just going to go ahead and hop over to Virginia, to the routers here. Okay, so here's a router. This is a 236.67 is the last 2 octets. It has 2,500 megabits per second of available bandwidth, but it's not eligible. So the TGW is labeled. I'll show you that. So here's the transit gateway, and I can look at its tags. And here's the auto TVPC cluster member with the value of TGW. Okay, so we know that's tagged. And we know that this router has the same thing. So what's going to happen is the puller is going to look at this. So 8, 9, 10, it just went. Let me go ahead and edit this. I'm going to make it eligible for VPNs. I'm going to go ahead and save that. And then I'm going to go into the other router and do the same thing and try and beat that 10-second timer. All right, here we go, 10 seconds. The poller's running, it's finding the routers, it's finding the tags, it's finding the TGWs, it's building all the VPNs that can be built into the 2,500 megabits per second per router. And it did it, and now it's configuring them. So we go back to the console here, and what we'll see, you should see new attachments. Okay, attachments pending, and the VPNs are pending, obviously, so they're being created. And there's 2 per router, and the reason that it's 2 is there were 2,500 megabits per second per router, just because they're C5 extra larges. And if we look at the tags, the tag is 0 now, and the tag is 0. And those VPNs are coming up. So it could be a little while. I don't know if this is even going to work still. Okay, so the tunnels have been created. They're still down. That's kind of the next step here. So it's going to take a little while. Okay, so the VPNs are being built. So what I'd like to do is go back over to Ohio. This is the attachment for App A, so it's pending. See if it's complete. Okay, now it's available. So now App A is attached to the transit gateway, and I'm going to go into that route table and put the default route to point to the transit gateway. Okay, so it's there. So now this ping should work. So now we have, through App B to App A and back, we have connectivity through the VPC attachments of the transit gateway. So now I'm going to go ahead and connect the routers in Ohio. And we're going to watch this happen. So this is 119.21. So if I go back here, the poller program is still running, 119.21. I'll make this eligible. Okay, 9:10. Okay, I just want to miss that poller and then save this. Okay, and then go here. Oops, not that one. So this should log everything that happens to it. Okay, so the program is finding the router and finding the TGW, and it's creating 4 VPNs because this had the capacity for 5 gigabits per second, and each VPN is 1.25 gigabits per second. And this is just showing on our terminal all the commands that are going in here to make this work. So right now, I'm using CLI and Paramico to program the routers, and the only reason I did that is because so many customers have older version of CSR1000vs out there, and just in case they had the old ones, I just wanted something that worked even with the older versions, like the 3.x. iOS XE. But in the future, well, I actually have built this with the netconf client, the NC client for netconf, and I think that's the way I'm going to do it in the future. Although my next iteration will be to do this with SD-WAN. So let's see. So this is built. All right, still down. So what happens is once these VPNs are built, it just takes them a while to spin up. So if I look at my VPNs, we'll see some pendings here. Yeah, so here we are. I'm going to hop back over to Virginia and see how these VPNs are coming along. Still pending. Sometimes the state doesn't update, and they've already come up. So I'm going to find that Virginia. All right, so here's the Virginia router. Okay, look at the tunnel interfaces are now up in Virginia. This is one of the first ones we did. Okay, and this router has 4 tunnels. All right, so there's 2 VPNs that actually go to this, but there's always 4 tunnels because when you build a VPN, Amazon actually builds 2 tunnels, and both tunnels are anchored in different availability zones for the VPC. And I'm sure it's the same with these VPNs for the transit gateway as well. Okay, so we just haven't received any prefixes. And what should happen is if I go to Virginia, we can look at the transit gateways route table, and what we see are 2 VPC associations, and those 2 VPCs should be propagating too. So the VPC routes should be in this table, and here they are. So this is VPC, or the app C VPC, and this is the app D VPC. They have been propagated, so I expect those to show up in the route table. This is Ohio. Let me go back to Virginia. This is Virginia. Okay, so BGP, looks like the adjacencies are up. Okay, look at here. Now we have 2 routes. So those 2, 10, 255, 064, and .80. And we should get that from all of these. So this means that this router will have 4 different ways to get to 4 equal cost multipath ways to get to these 2 networks. So let me just show IP route, VRF internal. So right now with the 2 neighbors that gave us the 2 routes, we see those right here. And as the routes are learned from other ones, then there will be more. So it's still 2. Okay, so the VPN are still coming up. But this is what's interesting here, is that this 10.1.16 and 10.2, this is app A in Ohio, and this is app B in Ohio. And it's coming from one router right now. So this is the inter-region connectivity through one router. There will be the other one too. Okay, so we should receive more routes. So these 2 peers have yet to share the 10.255 routes. And we have one path to get to the 10.1 and 10.2 right now. But the good news is that this is app A, and we have a 10.0.1.1.27 for its internal network, and this one's actually on internal. So 10.255.0.69, I should be able to ping inter-region So app C is going to go from Virginia to 10.1.1.27 in Ohio, and it can do it. So inter-region connectivity is there, and these are still coming up, these VPNs. So these haven't come up, but if I jump over here, so now I'm in Ohio. Tunnels are up. Oh, so many different peers. So all of these VPNs, and there should be one, two, there should be, well, there's 4, so there's 8 total, 8 tunnels, and this router is receiving 2 routes from each. So show IP BGP. And here's the networks for that. This is app A, this is app B, and these are all the different tunnels. It knows how to get there, and the small m is for multipath, I'm pretty sure. There it is, multipath. Okay, so inter-region connectivity, everything is there. And what I want to show you now is, let's say, well, I could shut down a router, I could terminate one, but what I'm going to do is go into a router, like the one we were just on. That's Virginia, not this one. This is .21. I'm just going to mark it as not eligible for VPNs, and what we'll see is the poller will remove the VPNs. This would be the same as if I shut down the router, but we wouldn't be able to see the commands getting pulled out. So I'm just going to go ahead and change the tag here to not eligible. I could put anything, but I'll put false. The program only looks for true. And I'm going to change it from true, so now it won't be eligible. Okay, so I missed this iteration of the poller program. Here's 10 seconds now. We should see all the VPNs being deleted. So the 4 to it have successfully been deleted in Amazon. And then if this can contact the router, like if it was stopping or shut down, it wouldn't be able to. And which isn't a problem. If it was terminated, obviously, because it was shutting down, it wouldn't matter because you would build a new router with new configs. If it was stopping and it deleted the VPNs from stopping, what it would do is make entries, zombie entries. And if the router came back up again, the good news is that this program, when it tries to make new VPN tunnels, it actually looks at what tunnels are already there and what CIDRs are already used, so it won't overlap it. And there will be logs that show the issue. So what I'm going to do is leave this poller running. And now if I show IP interface brief on this one, the tunnels are on. I'm going to begin router BGP here. We'll see that all of the different neighbors are gone, and there was quite a few of them. 8 of them, in fact, and they're gone. So everything's cleaned up. And if I just show run, the policies and IPsec policies, they're all wiped out there too. There was quite a few before, so. Okay, so that's cleaned up. So now, let me move this, and I'm going to take a look at the other router. If I can find it, that's app A, B. That's a Virginia router. So this is the other Ohio router. So if I show interface brief, it's 250. Oh, I never brought it up. Okay, so we'll go ahead and make this true. So we'll get some configs very quickly on this within 10 seconds. Okay, so the polar ran. It's taking a look at, once again, the CIDRs and the interfaces, so there isn't a conflict. It's programming it. So it's going to have its 8 different VPNs. And I'm not going to wait for the VPNs to come up. It's going to wait for this programming to finish. Okay. Show run here. What we'll see is there's all these IPv2 profiles, and we have the IPsec profiles. We have all the different tunnels built, and then the BGP neighbors are here. So once again, Amazon will try and bring these up, but what I want to show is if I shut it down. Let me find where we are on the, okay, we're at 3, 4, 5, 6, 7, 8, 9, 10. I'll go ahead and miss this polar loop. But now, what if I stopped this router? So the router is stopped. So the program's going to remove the VPNs because no need paying for these VPNs anymore. So here we go. All 4 have been deleted. And then it tries to reach the router to remove the configurations, but it can't. So this is what happens. Okay, there's a log file when this runs. So it's the TGW polar log. Oh boy, it's a long one too. Let's see. I guess I don't have VI set up. Not sure how to go to the end other than this. Okay, so it says the router, the interfaces that are there, the CIDRs that are there, and that's that. But it won't hurt anything because when I start it again, it will never overlap that. So these logs mean that you could go in and clean it, but the idea is that you don't stop it, just terminate it, and then use a program that builds a new one with all the proper configurations. And then the program will go ahead and build the VPNs it needs. If you want to remove a VPN and leave a router running, just mark the eligibility flag to false. So that's that. I shared this all on my my GitHub page. So this is out here. I call it AWS TGW to DMVPN polar. It has a README file, so this talks about how to install it. I recommend using the web program for the deployment. It's this one once again. Here, let me show you. It's the web, and what that is this here, where you can deploy clusters. You can extend to regions. You can add more capacity to any region that has the cluster there already. And I had shut it down already, so, oh wow. So I just added the TGW, and looks like I missed something. So this is trying to go to the classes, and it's trying to get the VPN gateway ID, and there isn't one because I'm using the TGW ID. So this isn't good. So what I'm going to have to do is, and that was for my VPN, TGW classes VPN, line 63. This is going to have to be an OR, because the VPN is either going to have this or that. It can't grab both. So this will be fixed for the web program for this. But this program just makes it really easy. All right, and that will be fixed. So there's the dashboard that pulls everything up. Then you can add clusters, add regions, add capacity, disable routers, redeploy routers, and there we go again. So I'm glad that happened because I'll be fixing it very soon. I actually just made all the changes to add the TGW, just because I wanted to show the dashboard. All right, yeah. So quite a few functions. I had to add a few things, and I haven't committed it either. So this part isn't in GitHub just yet. All right, so that's that. So this is shared on GitHub. If you need a secure and scalable solution for inter-region AWS traffic or AWS back to your enterprise, then this is one that it works. The polar works like a charm. I just did the web part, but that'll be fixed within the next probably 15 minutes. So, well, good luck with that, and thanks for watching.